All right. So in this video, I'm going to be explaining another important paper with the title Graph Kernels. This old paper in 2008. If you want to capture the local structure or semi-local structure or even global structure of a graph, you need to work on random walks. And there are many versions of random walks. But sometimes you can speed up, make it faster if you combine it with ideas of graph kernels. Because around each node in a graph, if you write the k-hop, neighborhood of that node, then this is a subgraph. Let's call it G1. Then there is another subgraph. It could be a latent graph that you should discover. We call them filter. Then you have another. So you want to see the kernel between these two graphs, how similar are these two. Because if they are similar to a particular filter, I use the analogy of convolutional neural networks so that you get the idea. So if we stick to some kind of filters, for example, this is just one of them, it could be another one, then you can capture the local structure very beautifully. And it's very, very, very fast as well. And also you can analyze it much easier than just random walk, because the length of your random walk could vary, and you have different variations of structures, different kind of structures. So that's why graph kernels are very important, especially in 2025. So we present a unified framework to study graph kernels, special cases of which include random walk graph kernel, marginalized graph kernel, and geometric kernel on graphs. Through extensions of linear algebra to reproducing kernel Hilbert space. For example, that what was that graph-led kernel? K graph-led kernel, that you do a dot product between two graphs. For example, F1 is the graph-led vector of one graph, F2 is graph-led vector of another. When you are doing this, it means you are going to a Hilbert space, and in that Hilbert space you are doing your calculations, which is easier to represent each node to its neighborhood subgraph, and you represent it by F1. Another node with another neighborhood subgraph, you represent it by F2, then dot per se. So you see how similar these two nodes structurally. And so this is a direct product graph, because you can create your graph kernel using this dot product between two graphs, G and G prime. So this is a dot product between, a cross product between the product between two graphs, G1 and G2. And this is G1 times G2. So this is kernel definition of that. If you do on the product graph, then they have these nice properties. This is a very important long paper that I just want to show that this is really interesting. And also we can see this relationship to the Apanov equation or Sylvester. So there are many techniques to calculate the kernels. Then they talk about geometric kernel. The computational complexity is cubic, which is high. So we want to find methods to calculate the kernel so that it could be at least linear. So they did their computations for these data sets that we use for graph classification. enzyme, protein. And they use different kernels like delta kernel, linear, and the composite graph kernel. For example, you have one kind of graph kernel and another one, you can just add it, you can create a composite graph kernel.